This is a series of 3 videos on statistical process control, which is how we take measurements and plan out for processes to try to, minimize defects that slip through and minimize our measurement costs. There'll be a lot of semiconductor terms that I talk about in here, so we can give you a link to what some of those things mean elsewhere. So these are the folks who developed control charts. And I really like this quote because it's very humanistic, right? So really, we want you to be able to understand SPC, and right now it's just be intuitively and kind of how to come up with your own control chart. And at the very least, be able to take data in lab and make decisions. So there's certain kinds of control charts. We're going to just, don't worry about the specific ones. We're just going to do simple examples. And yeah, it's like, what is our definition of quality? Are we meeting spec? Is it conformal? Degree of excellence? Some number. But hopefully, yeah, we'll be dealing with statistics. And the thing is it might seem counterintuitive, but the best we can hope for is some purely random variation in what we're creating. Because if there's a trend of any sort, that kind of means there's a problem that we need to fix. All right, and yeah, this is something that's important across the company. Even though people should talk to each other, sometimes they don't. And rather than having a gut feeling that something needs to be fixed, really statistical process control it's at least a process to making decisions. All right. This isn't a course in control charts, so don't worry about that. Okay. So how do we design a control chart? And I think what I want to do is just show you what one is. Hopefully at the very end. Okay. And so let's just say, what is a control chart? And this is X. And so here's this x-axis is some kind of sample measurement, right? It could be anything, right? It's actually looks like based on the number oxide thickness, right? So this is like this point here, X bar, is the average oxide thickness on a particular wafer. And then the next wafer, and this assumes independent runs where you're processing one wafer per run. All right, then this line in here with these squares is the grand mean, and it's the mean of all the samples, all right? And so depending on how you vary around the mean, you can make decisions about whether your process needs to be improved or to let it go. Then based on, sometimes it's the range, what's the difference, right? Sometimes based on the standard deviation, you get these upper and lower control limits. So there's rules that when you look at the points, as you plot things through, that will tell you whether you really have a problem or whether you don't. So that is a control chart, is you're measuring something over time, right? That when you look at it, in another talk, it'll tell you what are the rules. So anyway, we need to gather data. That means measurement. Measurement equals time and money, right? And so just randomly measuring something is another way of saying I'm randomly looking for a problem. It's kind of like in the health industry where they don't like to give you medical tests unless there's some kind of evidence that you might have an issue. Because there's a thing called the false positive, where if I just give you a test randomly, you might come up having a disease when you don't. So there's lots of reasons not to over measure things. Now, we need to have a variable, and really it needs to be something that has a number associated with it. And it shouldn't just be like, well, let's just measure everything, right? And that was big data. If we had enough data, we'd know everything. But, and even in AI, every input, right, might not actually be important to the output. But if you measure everything, even the things that have no theoretical basis can upset the model. So it's really better to know your process so that you can select the right variable or variables. Then there's subgroups. That's a more advanced topic. And then the size of the subgroup, right? They say 4 is a great, measuring something 4 times is, optimal. But 5 is easier to calculate, and in our wafers, if depending on where you are in our teaching sequence, you know that we take 5 measurements when we do a wafer, right? But sometimes measurements are very expensive, and you might ruin the very thing you're working on. So you might have to go for 2 or 3, right? Or you can go to 10 to 20. So you can't just say 5, right? That 5 comes out of years of experience, and actually semiconductor industry uses 5 as well. All right, so now at the company you want to say, how is it being done? Should we use a form, standard Excel, right? I like to use Python, students seem to like to use Excel, but we have to agree on where the data is stored, what each column means, things like, and how things will be measured. So it's in a sense standard operating procedures. So we have a process that makes transistors in 129, and really, as long as the transistor works, the learning objectives are made. We're not really trying to sell them. But we'd like to improve our process so that people could design circuits that make, that have a specification that you can actually predict. All right. So what do we need? So, a transistor process has many sub-processes, right? So each sub-process needs to be in control, which means there's no trend. The variance that's showing up is just random, right? And then the variance is small enough that we can reliably predict circuit performance. All right. Now, yeah, what are other decisions? In class, we measure oxide thickness a lot, and you might have seen this already, that it can take a long time, especially if you want to take 20 points per wafer, right? And you've got 50 wafers, that's a long time. So, can we reduce the amount of measurements, right? That reducing inspecting costs, right? Right now we have shapes that overlap each other by 8 microns, right? To prevent device failures. That would be another process, but it'd be nice to know, do we really need 8 microns to get 99% reliability, or could it be 5, right? We need to verify a design rule, right? And yeah, what is the other objective of engaging in this is we need to learn control charts. Now, yeah, what variable in a transistor process? There's the thickness of the wafer, the starting resistance, you know, the resistivity of interconnects, the resistivity of the interconnect, um, widths and lengths, right? So that's just for one 4-mask NMOS process, right? And I'm sure there's more. So trying to measure everything, right, might not just work, even in our situation, because we really, we have about 2.5 hours a week in lab. So time is very important. Right now, in a semiconductor fab, time is important because each piece of equipment is costing the company a lot of money. Inspection usually takes that wafer and stops it from being processed while you inspect it. So that's money going out the door during inspection. So this is a current mirror. Not going to explain it, but it's essentially we can set up a transistor here to supply current, which sets up a voltage on this, and that whatever current is going through here should go through here. And it's a classic analog design. And here are all the device physics equations that go into that. All right, threshold voltage is important. So if we sweep a DC input and we're stepping current here, right, you can see that there's a region of relatively flat current. But just in this plot, I'm changing W and L, right? You can see how much the current is changing with width and length, which ID saturation is the width of the transistor divided by the length, right? If the threshold voltage is changing, you can see that there's a square law dependence on that. The oxide thickness is changing, right? So any change in a parameter will change that current. This is just a simple resistor, right? And you have length, width, and resistivity, which will you need to get into a tight specification. This is our MOSFET. This is more device physics. You don't really need to know it for this talk, but it is what I'm trying to give you all the equations of how these parameters affect transistor performance, but that's not really important for this talk. Okay, so the circuit designer, right? They control how big the transistors are and how things are connected. The process designer, right? How thick is the gate oxide? What is the doping? What is the junction depth? These are other things that the process, you might not control it, or you might mitigate it, or you might minimize it, but that's what the person designing the process cares about. Okay. And still, at the end of the day, we need to decide a variable. And one of the best variables to measure is oxide thickness, because that's when the transistor turns on and you have C-ox here and the oxide thickness is in there. All right. So we're going to measure oxide thickness across the wafer subgroup 5, because that's we've been doing that a long time. Now, each run in the furnace isn't necessary. Those wafers aren't independent of each other, right? So I might have 50 wafers going in the furnace at the same time, but the variance across a boat isn't necessarily random. So you might take the average of all the wafers on a run, and that becomes 1 point. So if you have 10 wafers, 5 points, 50 points, the average of that and the range of that becomes 1 point on your data, on your control chart. Okay. So what we have here is, this is position, right? in the boat, right? First position, second, third, fourth, fifth. And then here we have top, center, bottom, left. And ideally, it would look kind of random, right? And not varying, across the boat or top to bottom. But there is some. So that is a case for basically taking this thickness and finding the average of all of these points and then either doing the standard deviation or the range. So now we're back to this control chart. So we have one now isn't position one in the boat, it's run one, where you cleaned the wafers, loaded them, grew the oxide, took it out and measured it, right? Every wafer that in that run. And so that would be the mean of each run. Okay, some days it's up, some days it's down. And then and then you can use these upper and lower control limits to make decisions about whether it's a control or not. And that's a later talk. All right. Then we did range, which is the range rather than the standard deviation. And RB is the average of the range. Now, the smallest the range can be is 0. It doesn't go negative. So 0 is standard, right? That's by definition. And then the average range is what? About 36. And so then you can see how the variation from run to run is going, right? This might be a problem here. Anyway, that's that control chart slides. Then we have a more specific example, okay, where here's our wafer. We have 1, 2, 3, 4, 5. And now for this example, one wafer is processed at a time. So the lot is 1 rather than, 10 wafers like our furnace and 5 points per wafer. And then you take the measurement thickness, position 1, 2, 3, and then you would just enter in the data. And so that's why the Filmetrics will do this for you, but you have to be very exacting about this, because if there's anything wrong or a typo, it throws everything off. So the first thing you do is calculate XB, which is the average of all 5 positions, okay? Then you calculate the range, like what is the high, the highest, largest, the thickest thing minus the thinnest thing, right? And then that gives you the range. Okay, and you just max from min, it's always positive, okay? Then the grand mean is you just take the average of each one and average it. And that's the middle of the control chart, okay? And then you do the same thing for the range. Now, if the sample size on each wafer is 5, this factor here is the range times 0.58. There's lookup tables for this, and the lower control limit is that. Okay, and then the range has its own equation. Okay, so XB is the average, meaning each one of these was one run because we had a single wafer processing, and we took the average. So the average of run 1, the thickness is this. The average of 110 is above the control limit. Now, statistically speaking, that could happen. It could be a random variation. Right? Just because something is 6 sigma away doesn't mean the probability is 0. It could happen. But you would then have to make a judgment call. Was that a typo? Was that a bad run? But that would be something worthy of investigating. But right now, we're just saying something must be wrong, so let's take it out. And so now we have our upper control limit, lower control limit, and then our mean. And you can see that these are, like here, 1, 2, 3, 4. It's jumping around the line. 1, 2, 3 going up. 1, 2, no, only 2 in a row going down. So it's actually in control. And the same, now we have the range, right, which is like the standard deviation. It has its upper and lower control limits and the average of the range. And you would just look at these points to tell you whether it's in control or not. So those are like the trial limits, meaning we only used, so much data to create our control charts. Then we add in the rest of the data. In a way, it's like training an AI model, right? If you use all your data to train the AI model, it'll be overtrained, right? So we started off with like 15, and then we added the rest. And, from I, it looks okay. The range, yeah, there's a few out of range, but at 100 points, yeah, the probability of that happening and it not being a problem is not 0. Okay, but on the other hand, maybe we needed to use more data to train it. 15 wasn't enough. Maybe we need to use all the data we have, right? So we used all the data we have, and now it looks good, but we can't really say if the process is in control. We have to keep using the process and see what happens in the future, okay? And again, we're still, trying to be somewhat intuitive with this. I can understand, right, that this is not easy. So now we talk about, is it in control? Is it out of control? Is it random? And then we have statistical process rules, and these come from Western Electric. So we talk about those control limits like sigma, which is like a standard deviation, right? So if you have 1.3 sigma away, it's worthy of investigation. You can't say, though, that it's out of control, right? That's the thing people don't like about statistics, is they don't really tell you if it's bad or not. It's just worthy of investigation. Is there a relationship, or let it be. Now, if you have 2 out of 3 points outside of the 2 sigma, you could have a problem. 4 out of 5 out of the 1 sigma, you could have a problem. 9 consecutive points on the same side of the center line, 6 going up or 6 going down, and then like you're trying to see something oscillate, right? And then 15 in a row inside 1 sigma. So now if we look at this, right, we have 1 on the control limit, right? And just this is 3 sigma, this one is 2, that is 1, right? So how many points in a row are inside the 1 limit? So we'll count that one as being there. 1, 2, 3, 4, 7. So that's 7 in a row. 1, 2, 3, 4, 5, 6, 7. Yeah, so let's go back. 9 consecutive points on the same side. So no, we didn't violate that rule. 2 out of 3 consecutive. So here's a 2 sigma control, and actually there's only 1 out of it, right? So that's not a problem. 4 out of 5 out of the 1, I think we already calculated, right? Or no, here's 1. Okay. Here's 1. Right? And then inside 1. No, see that one doesn't count. So it's really 1, 2, 3, 4, 5, 6, 7. So this idea of 9 inside, 9 on the same side, that's not it, right? So 9 points on the same side. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yeah, no, it's not working. So this looks like it to be in control. Okay. Oops, sorry. Any errors? Now here, right? Hey, this one is much higher. Right, so there could be a problem. Doesn't mean there is, but it's something we have to look into. And then here, I have to go reread the rules, okay? But I'm thinking not. 1, 2, 3, 4, 5, 6, 7. No. Anyway, now here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All the data points are within the 1 sigma line. Okay, so 9 consecutive points on the same side. 15 consecutive points inside the 1 sigma. So 1, 2, 3, 4, 5. Or go all the way to the end. So they all are. There's 20 points. So yeah, what happened is that the range must have changed to be something smaller. So even though the variance is smaller, and you'd say, hey, that's great news, that process has changed, right? Or there's statistical evidence that that process has changed, all right? So it would be out of control. This is just a brief introduction. Just to get you started. And I think actually having some tutorials with known data, creating your own data, creating your own control chart, and then some sample graphs that are in control and out of control, then that'll really help you learn it.